If homologous series always seemed confusing, this might finally make it click.
Hey everyone, and welcome to this explainer. Today we're going to unlock a pretty fascinating mystery hidden deep down in the microscopic world. We're looking at how the invisible architecture of atoms literally dictates the physical reality of the stuff we touch every single day. So if you're a focused learner looking to totally master the physical properties of chemical structures, you are absolutely in the right place. Okay, let's dive right into this. There's this massive paradox in chemistry, right? We know covalent bonds involve sharing electrons between nonmetal atoms. That is the baseline rule. But if the fundamental mechanism of sharing electrons is exactly the same, why do we get such wildly different physical results in the real world? I mean, why are some covalent solids incredibly soft and super easy to melt, while something like a diamond, which is also covalent, is famously known as one of the hardest, most unbreakable substances on Earth? Well, here is our roadmap for today to figure that out. We'll quickly cover the covalent paradox, the difference between islands and continuous fortresses, why intermolecular forces break, an ultimate structure showdown, and finally, how to nail your chemistry exam. So, starting with the covalent paradox and those two wildly different outcomes. It's honestly incredible that a single bonding mechanism, just atoms sharing their outer electrons, results in exactly two completely distinct types of structures. It's not a sliding scale here, it is literally a fork in the road. Let's walk down that first path. The first outcome is what we call simple molecular crystals. Now, the absolutely crucial distinction here is that the strong covalent bonds only exist inside the individual molecules. Think of it like a tiny, tightly knit group of atoms. But the forces connecting one whole molecule to the next one, those intermolecular forces, are incredibly weak. And because the connections between the molecules are so flimsy, the substance overall just completely lacks physical toughness. This gives us solids that are generally soft and have super low melting points. Now let's look at the second outcome, giant molecular crystals. This is a massive contrast to what we just saw. In substances like diamond, those strong covalent bonds don't just stop at the edge of some small molecule. Nope, they extend continuously throughout an entire massive lattice structure. Literally every single atom is locked into its neighbor with a strong bond, creating this endless, three-dimensional grid. And that continuous network is exactly what creates Earth's hardest materials, giving them incredibly high melting points. Okay, let's talk about islands versus continuous fortresses to really build out this microscopic world. This brilliantly illustrates the difference. Imagine a simple molecular structure as strong, impenetrable islands. Those are the molecules themselves. But to get from one island to the next, you have to cross these incredibly weak, rickety rope bridges. Those are your intermolecular forces. Now, on the flip side, the giant molecular structure has zero islands and zero bridges. It is just one massive, continuous, interlocking fortress wall made of solid stone. Every single part is strongly connected to every other part. Right, so why do those intermolecular forces break? That's the secret to melting. What are the actual practical consequences of these two different architectures? Well, when you try to melt a simple molecular crystal by turning up the heat, only the weak bridges break. You aren't breaking those strong covalent bonds inside the islands. You just need enough energy to snap those weak, flimsy rope bridges connecting the islands together. And since breaking weak bridges takes barely any energy, simple molecular substances melt at really, really low temperatures. Conversely, look at what happens when you try to melt a giant molecule. You don't have any weak bridges to target. To melt a diamond, you have to literally break down the fortress wall. You have to apply massive amounts of thermal energy to sever those continuous, super strong covalent bonds stretching throughout the entire giant lattice. That is exactly why the melting point of giant covalent structures is just so off the charts. Let's put this into an ultimate structure showdown and ground our analogy in some actual data. Now, what's really interesting about this is we're bringing in a third player, ionic bonds. This gives us a really complete picture. Look at the melting points. Ionic bonds, like sodium chloride, have high melting points because of the strong electrostatic attraction in their lattice. But giant covalent structures, they are very high, even higher than ionic, all because of that continuous network of strong bonds. Meanwhile, simple covalent structures are way down at the bottom. And for hardness, ionic structures are hard but brittle. Giant covalent structures are extremely hard. Again, think of that diamond fortress. And simple covalent structures are generally pretty soft. So you see, the microscopic reason for the strength directly maps to the macroscopic physical stuff you'd measure in a lab.
All right, let's talk about nailing the chemistry exam through strategic application. Understanding all this theory is fantastic, but let's pivot to the practical payoff. Here's an exam tip so you know exactly how to use this knowledge to absolutely crush your CSEC tests. Examiners are actively checking if you can differentiate between these physical properties in a test setting. So the crucial point is this. If a question asks you to distinguish between ionic and molecular solids, do not just ramble on about the theory of electron sharing versus electrostatic attraction. No, examiners want to see you reference two specific pieces of evidence. Number one, melting point data, which we just thoroughly covered, and number two, conductivity data. Using those two specific, observable traits is the primary strategic way to prove you truly understand the difference in bond and interaction strengths. To wrap up this explainer, let's bring it all the way back to your actual physical reality. Look around your room right now. Just pick an object. Based on how hard it is or what you guess its melting point might be, can you start to visualize its microscopic bond structure? Are you looking at weak bridges connecting strong islands? Or are you looking at an unbreakable fortress wall? The microscopic world is entirely responsible for the physical one we interact with every single day. Keep that visual locked in your head, and you will never forget the difference between simple and giant molecular crystals. Thanks so much for joining me on this explainer, and keep learning.
As always, the link for this study tool is in the description below. Let me know what you think in the comments.